Hi guys, have you ever wondered how the bank decide whether to approve your loan, or how an insurance company estimates the probability that a customer will file a claim, or how investors build models to predict whether the company is likely to default? Notice something interesting. None of these questions ask how much. Instead, they ask will it happen or not. That changed everything. Traditional linear regressions were designed for continuous numbers like revenue, stock return, or GDP growth. But when the outcome is simply yes or no, default or no default, pass or fail, we need a completely different tool. That tool is logistic regressions. In these lessons, we will build the institutions behind logistic regressions from first principles, understand why finance professionals use it so often, and learn how it differs from ordinary linear regressions. So let's begin with the problem. Suppose you are a credit analyst. You want to predict whether the company will default on its debt over the next year. There are only two possible outcomes. Either the company defaults or it doesn't. There isn't a value of 0.43 defaults. The outcome is categorical. More specifically, it's binary. Now think about using ordinary linear regressions. Linear regressions can predict any real number, -2, 150, or even a probability greater than 1. But probabilities must always stay between 0 and 1. That's the first major problem. The second problem is that the relationship between explanatory variable and probability is usually not linear. Image increasing a company's debt ratio. At first, default probability may rise only slightly, then it accelerates. Eventually, it levels up near 100%. That curve relationship cannot be captured well with a straight line. So we need a model specifically designed for probabilities, and that's exactly why logistic regressions exist. Before introducing the mathematics, let's understand the dependent variable. In logistic regressions, the dependent variable is qualitative, sometimes called categorical. Instead of measuring an amount, it classifies observations into groups. For finance, these groups are often binary. A borrower either default or survive. A customer either churn or stay. A trade either succeeds or fails. Think about a security checkpoint at an airport. Everyone who walks through is classified into one or two groups, approved or selected for additional screening. The system isn't measuring how much someone passed, it is making a classification. Logistic regressions work in exactly the same way. Its goal is not to estimate a number, its goal is to estimate the probability that an observation belongs to a particular category. That probability becomes the foundation for decision making. So now we arrive at the heart of logistic regressions. Instead of modeling probability directly, we first transform it. Let's build this step by step. First, we start with a probability we call it P. This could be the probability that a company defaults or the probability that a loan is approved. Next, we convert probability into odds. The formula is odds equal B divided by 1 minus B. Think about odds as comparing to possibility, the chance that event happen versus the chance it does not happen. For example, suppose default probability is 80%. That means probability equal 0.8. So odds equal 0.8 divided by 0.2. which equals 4. In other words, default is 4 times as likely as no default, but odds still aren't ideal for regressions. They range from 0 to positive infinity, so we go one step further. We take the natural logarithm of the odds. This gives us log odds, so we call it the log. Here's the beautiful part. After this transformation, the value can range from negative infinity to positive infinity. It's exactly the kind of variable that regression model handle well. This mathematical trick is what makes logistic regressions possible. Now let's combine everything. Instead of modeling probability directly, logistic regressions model the log odds. The equation looks very familiar. It resembles ordinary linear regressions, except the dependent variable has changed. Instead of y, we model the logarithm of the odds. Each coefficient tells us how much the log odds change when one explanatory variable increases by 1 unit, holding on other variable constants. Notice something important. The coefficients no longer represent change in probability directly. They represent change in log odds. Only after estimating the equations do we transform the results back into probabilities using the logistic functions. The final probability equations always produce value between 0 and 1. That's the one biggest advantage of logistic regressions. No impossible probabilities, no negative probabilities, no probabilities greater than 1. The model naturally respects the rules of probabilities. So now, let's move from mathematics to investing. This is where logistic regressions become incredibly valuable. Suppose a bank has financial data for 100,000 borrowers, income, debt ratio, credit history, employment status. Instead of predicting future income, the bank wants to predict one thing: will this borrower default? Logistic regressions estimate the probability. Perhaps the model predicts a 3% chance of default, or maybe 45%. These probabilities directly influence lending decisions. Investors use the same idea. Credit analysts estimate default risk. Private equity firms evaluate bankruptcy risk. Insurance companies estimate claim probabilities. Fraud detection system classifies suspicious transactions. Note the buttons. Whenever the outcome is a classification rather than a continuous number, logistic regressions is often one of the first model professionals consider. So remember, linear regressions explain continuous outcome, but logistic regressions estimate the probabilities of discrete outcomes. Once you understand that distinctions, the formula become much easier to remember because they solve a very practical problem faced by analysts every day. Thanks for watching.